All right, so in the last video, we introduced logarithms for the very first time and just the very, very basics. What is it? And what does the notation for it look like? And that's where we started in the last video. Okay, this video, we're going to take the next baby step with logarithms, and we're going to approach some of the exact same concepts, but from the reverse perspective. Okay, so what do I mean by that exactly? Well, let's let the video get started and you'll see what I mean. So let's begin with our learning objectives, like usual. 3 learning objectives in this. First of all is another notation learning objective. So I mentioned in the last video that there are 2 kind of shortcut or shorthand pieces of notation associated with logarithms. I'm going to introduce the first of those 2 things in this video here. Then the second thing, in the last video, we switched from exponential notation to logarithmic, and from exponential graphs to logarithmic graphs. In this video, we're going to do the other way around. And then last but not least, we're going to talk about how to evaluate a very simple type of logarithm. And by simple, what I mean by that are problems where the numbers are small and convenient, numbers that you should be able to figure out without too much extra work. Okay, so with all of that said, let's get started here. The first thing I want to do before we actually get into the learning objectives is introduce a little bit of background about learning objective number 2. Okay, so we know from back in the day that when we work with power expressions, like say, for example, if I've got something that's being cubed is equal to 8, we know from back in the day that you can take the cubed root of that, and that'll enable you to figure out what x is. Okay, but we also know from back in the day that the flip of that works too. If I have the cubed root of something and I'm not sure what it is, let's just say this time it equals 3, then we know that the inverse works the other way around. So just like the cubed root cancels out the cube will cancel out the cubed root. And so I can figure out what x is here just simply by taking 3 and raising it to the 3rd power. So 3 times 3 is 9, times 3 is 27. So inverses work both ways. I can use the inverse, the cubed root function, as being the inverse of the cube. I can also use the cube as being the inverse of the cube root. It works both ways. And so that's what we're getting into with learning objective number 2. In the last video, we took exponentials and converted them into logarithms because logarithms are the inverse of exponentials. But it works the other way around as well. We can take something that's a logarithm and switch it into exponential form because exponentials are the inverses of logarithms. Okay, so with that little bit of a background, let's take a look at some of these types of problems. So in yesterday's video, or the last video, in the previous video that we watched, I think there's supposed to be an A in yesterday someplace, but that's okay. We did a problem that looks something like this. Say I have 5 raised to the x is equal to y, and I wanted to rewrite as a logarithm. Okay, then what we said was that we start by writing log. We make the base of my exponent match the base of my log. And then the thing that was my answer becomes the input. The math word would be argument, whatever, the input. And the thing that was my input, that becomes my answer. Okay, but now today we're going to do the exact same process in reverse. So we're going to rewrite the log as an exponential. Rewrite the log as an exponential. So now we're going to start, and I'm completely changing the problem. This has nothing to do with the problem I just wrote. We're going to start with some other log, and we're going to convert that into an exponential. Okay, so it's the same thought process in reverse. So first of all, I'm going to have some sort of exponential term, and the base of the exponential term needs to match the base of my logarithm. So here I have a log base 3. So that base is going to be the base of my exponent. Okay, but what's going to happen is my input is going to switch and become my output. So that's going to be equals, that's going to be my output. And the thing that was my answer, that is now my input. So it's the same basic idea, it's just everything switches, okay? So we can do that with equations that have variables. We can also do that with equations that have numbers. Okay, so here's an equation that has numbers. It's in logarithmic form. But now what we want to do is we want to switch it to be something that is in exponential form. So I'm going to keep the same base, log base 5, log base 5. The thing that was my answer, or the thing that was my answer becomes my input. So my answer becomes my input. And the thing that was my input, that becomes my answer, right? And with numbers, it's almost a little easier this way because this is something we know. We know what 5 squared equals. We know that 5 times 5 equals 25. So when we're working with numbers, as long as the numbers are simple and fairly straightforward, we ought to be able to check ourselves. So this would be the idea of switching from an exponential equation, switching from a logarithmic equation into an exponential equation. Okay. Now, we can also do that with a graph, okay? So I just happen to have a graph here. And what I'm going to ask you to do first is pause the video to copy this graph. And once you've got it copied, then start the video back up again and we'll resume this process. All right, so hopefully you've got my first graph here copied down and in your notes. And what we're going to do on here is we're going to use the graph. The way this would be written in a generic form in the homework is it would say use the graph of f of x. And so this over here, this would be f of x, okay? So we would be saying log base 2 of x plus 3. That's what f of x is, okay? So we're going to use that graph to create or to make the graph of the inverse of f of x. So that's what I've got here. This would be the inverse. So the inverse of f of x. Now, in this case, as a side note, I've shown the equation here. We know about the graphs of exponential functions. So this is probably a graph that we could make without even using this as an example. Okay, but the purpose here is to talk about how to use the property of an inverse to switch this into its inverse graph. The other thing I'll mention is the fact that 2 to the x minus 3 happens to be the inverse of log base 2 of x plus 3. That's not something that I would expect you to be able to figure out on your own at this point in our class. So if there's ever a time where you need the equations of the inverses, at this point in the class, I would give you those equations, all right? So don't get too hung up on the equation. Right now, let's just focus on, like we did last time, how do I take the graph of something and turn it into its inverse? Well, that doesn't change. If I'm working with exponentials and logs, or whether I'm working with other types of graphs, it's always the same. My x's and my y's switch. So this graph has an asymptote at x minus 3. That means the x is going to switch into a y, and my new function is going to have an asymptote at y equals -3. So there, I go from having a vertical asymptote to having a horizontal asymptote. All right? Now, all of these coordinate pairs are going to switch the x and the y value. So let's start with this one. I had an x value of 5 and a y value of 3. Those are going to switch. So now I'm going to have an x value of 3. So I'm over 3, 1, 2, 3. And I'm going to have a y value of 5. So I'm up 5, 1, 2, 3, 4, 5. And now I'm right here. Okay, so that basic process, like we did in the last video and like what we've done with other functions, that's exactly the same. So if you haven't already, I kind of forgot to mention this a second ago, you might want to pause the video and try and finish this on your own, okay? Once you've got it finished, then you can resume the video and you can check your answer against mine. And if you're already finished, then hold on for just a second and I'll keep going. All right, so at this point, hopefully everybody's finished with the graph. And the way you should have finished is by just moving right down through the list of ordered pairs and taking each x, y, and switching them. So this would have a x value of 2 and a y value of 1, because I switched those. Here I'd have an x value of 1 and a y value of -1, an x value of 0 and a y value of -2, an x value of -1 and a y value of -2.5, and last but not least, an x value of -2 and a y value of -2 3/4. And so I end up with my graph, knowing that there's going to be this asymptotic behavior. So I know that's going to keep going towards the left. And towards the right, I'm going to have this exponential growth. So it's just going to take off and head towards infinity. And so that would be my graph. Now, if you think back to what we did in the last chapter about graphing exponential functions, this should make sense to us, right? Because we know we should have our basic exponential 2 to the x graph, which that's the basic shape, but it should be moved down 3 units. And that's exactly what we have here. So that should make sense to us. All right, now that takes care of our first learning objective, switching back and forth between exponential and logarithm graphs, and switching back and forth between exponential and logarithm equations. Okay, now I'm going to move on to our third learning objective here. The third learning objective was to evaluate simple logarithms. And this actually right here is a perfect one to look at because A, I would consider this to be a simple logarithm, and B, it models exactly the way we're going to evaluate them here at the beginning of our class. Now, we will learn some other ways that you can approach this later, but this is the way that I want to do this. So we would be given the question. So I'm just going to jump right into an example here. So I guess we could call all of this stuff up here was example 1. We could call our graph as being example number 2. So now I'm on to example number 3. Okay, so there we go. Example number 3. And it would say something like evaluate. And remember, evaluate, that just simply means find what the numerical answer is. So simplify things down until you get to just a simple numerical answer. All right, so evaluate the log base 5 of 25. Okay, some books would just write log base 25 equals what? And then you would figure out what the what is, right? That's how it would be written in some books. I tend to write the directions evaluate. But in here, the question mark is actually helpful to me because the way that we're going to do this first is we're going to switch it into an exponential expression. So you can do this physically on your paper and pencil if you want to. But the other thing you could do is you could just, in your mind, think about this process. This is the same as 5 raised to the question mark power equals 25. And now I can just think of this as a question and think to myself, okay, self, 5 raised to what power is equal to 25? Well, I know that answer. 5 squared equals 25. 5 times 5 equals 25. So therefore, if I just keep thinking a little bit longer, I'm going to know that it's 5 squared that's equal to 25. And so this is my answer. The log base 5 of 25 is equal to 2. That becomes my answer. Okay, so really evaluating a logarithm, at least as we're going to approach it here at the beginning of our class, evaluating a logarithm is really asking the question. In fact, let's write this down. Evaluating a logarithm, I'm just going to put log for logarithm. Evaluating a logarithm is really answering the question. And then here's our question. What power do I raise the base to? There's my base. So what power do I raise the base to to get this input as an answer. And answering that question is the way that we're going to evaluate logarithms, okay? Now, as you get familiar with logarithms, this becomes almost like memorizing fact families, okay? If you think back to when you were in elementary school, you would have done something along the lines of, I know that 3 times 4 is equal to 12, and so therefore, I know that 12 divided by 4 is equal to 3. Remember memorizing those fact families back in elementary school? Okay, well, this would be a very similar sort of fact family. I know that 5 squared equals 25. So therefore, the log base 5 of 25 equals 2, right? Do you see how that works? Just like here, I'm just simply switching my numbers. That's all that's happening is I'm switching my numbers, okay? So this becomes the basic approach we'll take for logarithms. Now, I know what you might be thinking. I thought this too the first time I learned logarithms. What if I have some numbers that I'm not sure about, okay? So let's suppose I'm trying to find the log, let's say the base 2 of, I just lost the number. I think it's 1056. Let me make sure that I remember that right. $10.24, that's my number, $10.24. What is that? I apologize for that little, I just lost the number in my head, so I had to find it real quick. Okay, so what does this equal? What does this equal? Okay, so again, I'm going to write down this whole process. Not that you need to write all of it, but I'm going to write down the whole process. Okay, so this is what's happening in my brain. It's not what I usually am writing on my paper. Usually I'm just doing all of this in my head, but this is what's happening in my brain. So I start with log base 2 of 1024 equals what? That's what they've asked me to do. Figure out what this equals. Then in my brain, I switch that into an exponent problem. So 2 to the what power equals 1024. Okay, so now I need to start figuring out, okay, 2 to what power equals 1024? Well, I'm not sure. So I just grab my calculator and I start going. So if I do 2 to the second power, that's equal to 4. 2 to the third power, that's equal to 8. 2 to the fourth power, that's 16. Okay. Now I can type this in as individual powers over and over and over again, but you can see that's going kind of slow. It's taking me a little bit of time to get there. Okay. Here's another option I could do. If I think of this question mark as being an X, then I can go to my y equals and I can type in 2 to the x. Whoops, 2 to the x. There we go. Okay, so if I just type this in as being an x in my y equals menu, now I can go to my table, and my table gives me all these numbers for all these x values. All I have to do is find 1024. Oh, there it is. There's 1024 right there. So what power was x? Well, according to my calculator, 2 to the 10th power is what 1024 is, okay? And like I said, you can just keep doing this process over and over and over again until you find the number that works. In this case, you would have to do it 10 times to get to that number that works, okay? So there's a way to use your calculator to help you answer this question. But now, once I have figured out what that question mark is, now what I do is I turn this back into a logarithmic expression. So my log base 2, now these two things switch, of 1024 is 10. And there we go. Now I have my answer. So what does this equal? This equals 10. All right. So that becomes the basic process that we're going to start with for evaluating logarithms. We're going to start with just an answer the question type of process. And answering that question could be based on things that you've memorized. Like we all know that 5 squared equals 25. Okay, so it could be based on things that you memorized. or it could be based on guess and check on your calculator. That's fine as well. All right, now that takes care of almost all of our learning objectives. Let me go back to our learning objectives for just a second. There's our method for solving simple logarithms. We've talked about switching back and forth. All that leaves then is this first one, a shortcut or a shorthand, I should say, notation with logarithms, okay? So this is just a commonly recognized thing in math that at the high school level and at lower level college courses, just everybody knows this, everybody understands this, okay? We'll call it an abbreviation is what we'll call it, except I'm not sure if I know how to spell abbreviation. Are there two B's in abbreviation? Abbreviation. I don't know if that's spelled right or not. An abbreviation. Here we go. An abbreviation. So if I have the log base 10 of something, okay, what we're focusing on right now is the fact that it's log base 10. That's the important part. An abbreviation for logarithms with a base of 10. An abbreviation for logarithms with a base of 10. Log base 10. So it doesn't matter what's here. Variables, numbers, it doesn't matter. Log base 10, that's what we care about. This is called the common logarithm. Okay, now that is a vocabulary term that you do not need to know for our class. There will never be a time in our class where I ask you to tell me what is the common logarithm. But here's what you do need to know. Because it is so common, in most math books and different various math situations, we just don't bother to write the 10. We just write log x equals y. That's simply what we write, log x equals y. We don't bother to write the 10. Log x equals y. So when we see this, we need to recognize that when the base is missing, we assume the base is equal to 10. When the base is missing, we assume that the base is equal to 10. Okay? So that's the common logarithm. Now, we're going to finish with a final example using the common logarithm, and then that'll be it for this video. We'll be done. So here we go, example number 5. Example number 5. Evaluate the common log of 1,000. Okay, so because it's common log, this is the way they'll write it. All right, so the first thing when you see this that you have to recognize is you have to recognize that the base is missing. Okay, that's the first thing you have to notice. Okay, then based on the fact that the base is missing, you need to realize that this means log base 10. Log base 10 of 1,000. Okay, that's what this problem means. And so now that's the question we'll have to ask. So then we switch it into a question. 10 raised to what power equals 1,000? Okay, now the common logarithms are really some of the easiest problems to work with because we know that when I multiply 10 times 10, all it does is add zeros on, right? So thinking back to stuff that we've learned before, we know that 10 times 10 is 100, right? 2 10s gives me 2 zeros. 10 times 10 times 10 is 1,000, right? 3 10s gives me 3 zeros. 10 times 10 times 10 times 10 is 10,000, right? 4 10s gives me 4 zeros. So this is something that we've learned before. So with common logs, the problems are pretty straightforward. I just need to count up how many zeros I have. This has 3 zeros. So I conclude that it's 10 to the third power that's equal to 1,000. If I'm not sure about that, I can always check it. 10 to the third power. Yep, I get 1,000. That's good. So therefore, log of 1,000 is equal to 3. And that's my answer. So all of this stuff is things that are happening in my head. This is what I'm thinking. This is the thought process I go through. I first realize, hey, I don't have a base. Oh, that means it's base 10. 10 raised to what power? Oh, I know a trick for that. Just count the zeros. Okay, so now I count the zeros. There's 3, so it must be 10 to the third power. If you want to, you could check that on your calculator, but then there's my answer. It was 10 to the third power. And that would be a problem working with the common logarithm. All right, so that takes care of this video. I appreciate your watching. Have a good one.